All right, chapter 8 is about gases. So I want to talk about some properties of gases. Talk about pressure. We haven't really talked too much about pressure and the units for pressure. In this chapter, we're going to be talking about several different properties. One obviously is pressure. We're also going to be talking about volume, which we've talked about. We'll be talking about moles, which is a lowercase n. And we're also going to be talking about temperature. Okay, temperature in this chapter, you have to remember this, is always going to be in Kelvin. Okay, if I give you a temperature in Celsius, the first thing to do is convert it to Kelvin. This is the big thing in this chapter. Everything is in Kelvin. Okay, if you're thinking to yourself, well, is it Celsius in this case? The answer is no. It's never Celsius. It's always Kelvin. And remember, the Kelvin temperature scale, equation is 273 plus Celsius. Okay, so if I give you a temperature in Celsius or give you a temperature in Fahrenheit, the first thing to do is to get it into Kelvin. All right. Then we'll talk about a few gas equations. We have several different gas equations. We have the ideal gas equation, and then we have what's called the combined gas equation, which combines a bunch of equations that famous scientists have found in the past. Talk about some gas laws. And what if you have a mixture of gases? So instead of just having a balloon filled with helium, what if you have a balloon filled with helium and hydrogen and argon? What's the information? What's the pressure, the volume, the temperature, the moles inside of that balloon? All right, most people find this chapter pretty easy. The math is pretty easy. So there shouldn't be too many problems. All right, again, just what is a gas? A gas is a substance whose molecules are not in contact with any other. They are separated by large distances. So you can see in the solid case, the particles are very close to each other. Sorry about that. Let's get that out of there. You can see that the particles, my goodness, the particles are very close to each other. You have, intermolecular forces between them. Liquids, you have a little bit of space. You can see a little bit of space. But gases, you have very large space between all of the molecules. Okay, they are not interacting with each other at all. Okay, so that is a gas, which you probably already knew. Let's talk about some of the gases. First of all, on the periodic table, very easy to find the gases. The gases are on the total right side of the periodic table. Most of the non-metals are gases. Okay, first of all, the noble gases, we know that. Hydrogen's a gas. Fluorine, chlorine, oxygen, and nitrogen are gases, right? Nitrogen and oxygen is what the air is made out of that we breathe, mostly nitrogen, 80% nitrogen and like about 19.5% oxygen with a little bit of other elements in there. Okay, so these are most of the elements, but again, very few elements are gases. These are some very common gases that we kind of come across. Probably the most common is like CO2. I guess like CO should be here. Hopefully that's not very common. We don't come across it too often, but it is around. All right, also ozone is a good one, which maybe should be on this chart. Ozone is a gas that is also kind of common. All right, so N2O is if you ever were in Los Angeles. I grew up in Los Angeles, and on smoggy days, even in Colorado sometimes, down like in Denver, when you have a very smoggy day, that brownish red layer of smog is most likely dinitrogen monoxide. All right, so these are just common gases that we see. All right, the kinetic molecular theory of gas. This is a famous theory that nowadays it's very common. It's kind of obvious stuff. It's stuff that we already know. But this was kind of groundbreaking stuff back, 100 to 200 years ago, and you kind of have to, understand it or we always talk about it when we talk about a gas. Okay, first of all, a gas is composed of molecules that are separated by relatively large distances. All right, we just talked about that. So because of that, gases are very compressible. Okay, so if you actually were to take a gas and compress it hard enough, you can actually eventually, you can put these molecules so close to each other that it actually turns into a solid. If you were to squash it, put enough pressure, you would have no more room, technically, in between any of the molecules. So technically, you can turn any gas into a liquid or a solid by the pressure. Like I'm sure you've heard there are planets in our solar system where they have like liquid CO2 as their rivers, or liquid oxygen as their rivers, or well, probably not oxygen, but like nitrogen or CO2 as a river, okay, implying that it's liquid. Well, how is that possible? Well, the pressure on that planet is so great that it's actually liquefying a gas that we would normally see as a gas on our planet. Okay, so it's all based on the pressures. All right, second thing is that gas molecules are in constant random motion. All right, they are moving in straight paths, colliding with the walls of the container and with each other without any energy loss. There's no loss of energy. This is an assumption that we have to make. All right, more frequent collisions are higher pressure. All right, so really what pressure is how many gas molecules are hitting on the side of the container. The more it's hitting on the side, the higher the pressure. The less it's hitting, because it has more free random motion inside of the container, the less pressure. You can kind of see this. If they are further away, you kind of have a smaller pressure. All right, if they're closer to each other and they're tighter and there's not a lot of space in between them, they're hitting the walls much more often, so you have a much greater pressure. So that's a second assumption. Again, more frequent collisions. You can kind of, this is a kind of a summary of it. More frequent collisions result in higher pressures. Right? These are great multiple choice type questions, by the way. The third theory is gas molecules do not exhibit intermolecular forces, neither attractive or repulsive forces. That means these particles just kind of come together. If they approach each other, they just kind of smash into each other and they bounce off. Perfect is like in billiards. If you think of a billiard ball, or pool, if you play pool, all right, in billiards, you have two balls. When you hit the cue ball into another ball, basically that ball's energy just kind of gets transferred, but you don't lose any energy in this case, and the balls just kind of bounce away from each other, or the gas molecules just, they bounce away. The average kinetic energy is proportional to the absolute temperature. Okay, notice absolute. What does this absolute imply? Absolute zero. Kelvin scale, just like what I said at the very beginning. Kelvin scale, Kelvin scale, Kelvin scale. Okay, everything is in Kelvin. Okay, and the energy is associated basically with the temperature. The higher the temperature, the higher the energy. The lower temperature, the lower the energy. Okay, so those are the four kind of theories of a gas. Okay, let's talk a little bit about units of gas and kind of how you measure gases. Pressure of a gas. All right, gas exerts pressure on everything they touch. That means inside of this container right here, of the paint thinner container, this is empty, by the way, the gas molecules are hitting on the sides and creating a pressure. All right, atmospheric pressure, that's the pressure of our atmosphere, is the pressure exerted by the Earth's atmosphere, and here's kind of an example. All right, this is a vacuum, okay, and they turn the vacuum on to remove all of the gas molecules. So all the gas is getting sucked out. So what's it doing? It's creating a vacuum inside of here. So the pressure outside is exerting a force onto the container, and it's greater. The pressure up here is greater than the pressure inside the container, so it squashes the container. Okay, like for example, if we were to go out into space and we didn't have a spacesuit, well, space has pretty much zero pressure outside in space. All right, it's a vacuum. So the pressure inside of your body would be greater than the pressure outside, and what would happen is your body would basically just expand. You would immediately expand because the pressure inside you is bigger, and you'd basically explode. Okay, kind of a cool trick, but I would not want that to happen to me. Okay, so that's why astronauts wear pressurized space suits. They pressurize it to 1 atmosphere so that inside their suit they are feeling a pressure of an atmosphere so they don't explode in space. Okay, the opposite is true if you go down into the ocean. The ocean, as you go down, creates a tremendous pressure. All right, all that water on top of you is pressure, pressure, pressure. So you have to be in a container which protects you. Okay. That's why they also talk about that if you do scuba dive and you go pretty far down, when you come up, you have to come up very, very slowly, because when you go further down, your body starts absorbing more and more oxygen. So when you come up, all that oxygen has to come out, and you don't want your blood in a way to kind of like like all boil in a way. It's kind of what it's talking about. It's where all the oxygen all of a sudden all comes out of your body because the pressure is much lighter, so the gas molecules are able to expand. So you do not want to get a bubble in your blood, so that's why you slowly come up in scuba diving. All right, so there's perfect life examples. So here's a physics equation. I'm not going to deal with it. I'm not going to have you do any equations with it. But basically, what is pressure? It's the amount of force per area. So how much force are these molecules exerting on a certain area of the container? Okay, so that is basically what pressure is. So here are some common units that we use. One of the most common units is pounds per square inch, or PSI. This is what we use. Okay, this is a English way of doing it. We don't do this in our class, but in real life, in our daily lives, we deal with like PSI. For example, our tires. Our tires roughly are somewhere around 30 PSI. They're about twice the pressure of atmosphere. Okay, if you look on the side of your tire, it'll tell you to fill your tire somewhere 32, 35, like PSI. It all depends on the tire and the car you're driving and all that stuff. Okay, so that's pounds per square inch. That's what the PSI stands for. The most common ones we're going to deal with is atmospheres, millimeters of mercury, and torr. These are the common ones. Okay, 1 atmosphere basically is the pressure. So all these are compared to the pressure at sea level. So at sea level, so if you're standing at the ocean, wherever you are, California or on the East Coast or Australia, wherever you are, if you're standing at the ocean, 1 atmosphere of pressure is being exerted on you. And as you change altitude, you start either increasing if you go down in altitude, or you get lower in pressure as you go up. All right. So 1 atmosphere is also equal to about 760 millimeters of mercury, which is this, which is also equal to 760 torr. Torr is named after a scientist. Torricelli was his name, but they decided to change it into millimeters of mercury. But people still use torr and millimeters of mercury. All right. For example, so if you're at sea level, you have 760 millimeters of mercury pressure exerted on you. As you go up in altitude, so we live about a mile up, pressure up here is about 650 millimeters of mercury. It's about 100 millimeters of mercury lower where we are than it is at sea level. If you ever go down to sea level and you have a cup of tea or soup or a cup of coffee, I don't know if you notice this, but it's so incredibly hot compared to what we drink up here. If you have a cup of coffee, I find coffee or like boiling water not to be very hot up here. All right, and that's because water boils at a lower temperature. All boiling is being able to break the break the intermolecular forces and have the water break above our atmospheric pressure. Okay, so the more pressure exerted on a liquid, the higher the boiling point. The less pressure, the lower the boiling point. So water boils at like 95 up here. 5 degrees makes quite a bit of difference. So like I said, if you have a cup of coffee or tea or soup up here, it's not quite as hot. If you go down to sea level, things are so much hotter. Okay, and that's because of the pressure. All right, so that's why they tell you to add salt into water to increase the boiling point, because the salt is very ionic. It holds on to the water much harder, so you're kind of creating a stronger intermolecular force with the salt. So it takes more energy in order to break those bonds, so it takes higher temperature. That's why you should cook your pasta in a little bit of salt. All right. But we are going to be using some pascals. A few of these inches of mercury, we will not be using that without a doubt. And bars and a kilobar, there's also a kilobar. Those are units that we kind of use a little bit, but like I said, atmosphere, millimeters of mercury, torr are kind of the common ones. All right, so how do they measure pressure? All right, a barometer, you've all heard of barometer. If you look on the news on the Weather Channel, they'll say, well, the barometric pressure is so-and-so. At sea level, it's 29.92. That's 29.92 at sea level, normal conditions. So if there's a high pressure coming in, obviously that goes higher. If there's a low pressure, it goes down. But basically it's a long tube and you've got mercury, and as the pressure is exerted on the mercury, it pushes it up and it goes higher or lower. So that's basically how a barometer works. Here's a manometer, which determines the pressure of gas you have. Same type of thing, except you actually have a closed container and you have a gas that exerts. So higher pressure, the more it exerts down, so this goes up. All right, And so if you want to fill up a gas or you want a certain pressure, and it's closed off up here. All right, these are just the tools in order to find that. All right, we're going to stop right here for the first videos, and then we'll get to the ideal gas law.